last week we were talking about change of variables. And I gave you a couple of examples to compute the formula for change of variables. The formula says if I have an integrating function f x y, okay, with respect to two variables x and y in a region R, I can change the variables from x, y to u and v by two functions. Say if x is equal to g of u and v, y is equal to g h of u and v. Then the way of changing the integrating functions is pretty easy. I just need to replace x, y to u and v. And then I have to worry about how the intervening region is changed under this change of variable. Right? So I have to change how this intervening region is changed. So I get a new intervening region from R to S. So R is a restriction concerning X and Y. S is a restriction concerning U and V. All right, so we have to change the variables from X, Y to U and V in the intervening function as well as in the intervening region. But also there's one extra factor coming, right? So that extra factor is X value of the Jacobi, partial X, Y, partial U, V, where it is Jacobian partial x, y, partial u, v is a 2x2 matrix, partial x, partial u, partial x, partial v, partial y, partial u, and partial y, partial v. So this is the formula we have. We practiced a couple of examples, but at the end of the class, we went through one question too quickly, so I want to look back to this one and get all the details. So that's exactly the same question we had at the end of last class. And we already decided we want to change variables. All right, we did draw the region, and then we can identify it as x simple or y simple, but it is too complicated. Instead of going that route, we decided we want to change the variable from x, y to u, v, two new variables. And every time we introduce new variables, we have to decide which role this guy is going to play, right? So we want to decide u is equal to whatever, v is equal to whatever, all right? So every time you introduce new pairs of variables, you want to decide which role or which formula it is connected to the O pair, right? That's fortunately the clear link between these equations, right? So if you look at these four equations as the boundary defining functions of x, y, clearly I want to have y minus x, my new variable u, y plus 2x as my new variable v. Am I right? Okay, so this change of variables is definitely going to be in the midterm on Wednesday. Okay, so it's definitely there. And I want to introduce u as my variable, which is equal to y minus x. V is the new variable y plus 2x. So these choices of new pairs of variables is pretty clear for this kind of problems. All the change of variables, usually it's quite easy to decide. I want to have new pairs of variables, and then this new pair of variables is connected to the O pair x, y in the following formulas. And these formulas are pretty easy to find. And then not only you have to decide u, v is related to x, y in this format, and also you have to decide how this intervening region is changed. All right? How this intervening region is changed. This R is defined by these four different equations. And then I need to decide the boundary or the defining functions for u and v. All right? And the only way to link the restrictions is to link the restriction for u, x, y to the restrictions to u and v. All right? So these equations are not only there for you to decide what the new variables are, but also to decide what the restrictions are for the new variables. Are you with me? Yes? You have to also look at this restriction to see how I can restrict u and v. And this is pretty clear as well. So u is going from 1 to 4, and v is going from 0 to 4. Am I right? And last class, people were confused how I come up with these 4 numbers, and they are actually connected back to the original restrictions about x and y. So this is equal to u, this is equal to v. So these two equations will give me the restriction u has to be bounded between 1 and 4, and this gives me v has to be bounded between 0 and 4. Okay, so with this introduction of u and v, I need to change the functions into u and v, and this is pretty clear. U is equal to 1 minus x, v is equal to y plus 2x. So this introducing function is this guy. And then I have this region in terms of u and v is going from 0 to 4 for v and 1 to 4 for u. All right? Yep.
When I did this exact same problem on the homework, the range was from 0 to 3 and 1 to 4. That's the answer from that exact same problem, yeah.
For the homework, online homework. Yeah, the online homework still randomly choose the numbers.
No, the numbers are the exact same. Oh, okay, I get it.
These ranges are chosen randomly.
Okay, yeah.
It's just a matter of measure. Yes. You can change this number to whatever number you want. Right? It's not a huge issue here. And then I needed to keep up with this range of 4 numbers. So 1 to 4 is going for du, so I want to have du inside. And 0 to 4 is for dv, I want to have dv here. Okay? But there's one extra factor coming when you change the variable, which is the Jacobian factor. So I have to have a partial xy over partial uv equivalent. All right? So I have to compute this 2 by 2 matrix, partial x over partial u, partial x, partial v, and so on. Basically, you have to take the derivative of x with respect to u and v, the derivative of y with respect to u and v. All right? So in order to do that, I kind of look at these 2 equations. But if you use these 2 equations, it's pretty awkward to compute the partial derivative of y with respect to u. Am I right? It's pretty awkward to compute that. You can't do that, but you have to solve for x and y first. Am I right? Only when you have an equation x is equal to whatever of uv, then you can take the derivative with respect to u and v. Are you with me? For these 2 equations, you can only take the derivative with respect to x and y, not the other way around. Yes? Yep. So that's why this Jacobian, this is what we have. Did we have a holiday last weekend? Oh, we have a holiday Friday, so you guys have some excuse to be not very responsive, but hopefully things can go better. So I have to solve these 2 equations and get a x is equal to something, y is equal to something. But these are all linear equations, so you can easily solve them. So x is equal to, so if I subtract these 2, I'm going to get 3x is equal to v divided by, v minus u. So x is equal to v minus u divided by 2. So if I multiply the first equation by 2 and add them together, I'll be able to cancel x. So y is equal to 2u plus v divided by 3. Okay? Well, you can spend a couple minutes to solve this linear equation system. It's not going to be complicated. So now I can get an equation of x with respect to uv. Only when you have this, you can compute the partial x, partial u, and the partial x, partial v. Yep.
Why is it divided by 3?
So let's say if I call this number 1, number 2. So 2 minus 1 is going to give me 3x is equal to v minus u, and that's where I get this equation.
Oh, okay.
Am I right? So I multiply by 2 to first equation plus 2. This is going to give me 3y is equal to 2u plus v. That's where I get the second equation.
Oh, okay.
Yeah? Or if you don't believe me, you can actually verify it by taking the difference between these 2, you're going to get u. You can add y plus 2x, you're going to get v. Okay? Anyway, this is a pre-calculus practice. So it's not the key focus here, but you have to be able to do that, right? Now I want to compute partial xy partial uv. And as I said, I have two pairs of bars to make it even clearer. I want to compute the Jacobian first. So partial x, partial u, partial x, partial v, partial y, partial u, and partial y, partial v. Again, I want to stress again this order of the 2 by 2 matrix. The first rule is with respect to x. Second rule is in y, first column is u, second column is v. Right? So this is the 2 by 2 matrix. If you really want to ask how I get this 2 by 2 matrix, we can discuss afterwards. But there are mathematical proofs to say this is indeed the factor you need in order to change the variables. You can mathematically verify that. But this is not the focus of calculus sequence. Calculus sequence is to learn and practice the formulas, not to derive the formulas. Okay? But I know a lot of you are interested in how to mathematically prove some results. It's beyond the scope. But anyway, so this is what we have to prove. We have to compute. Sorry. So partial x, partial u, what do we have?
Negative 1/3.
Minus 1/3, right? So minus 1/3 here. Partial x, partial v, 1/3. Partial y, partial u,
2/3.
2/3, and partial y, partial v, 1/3. Okay? So this is what we have. And then we compute the determinant. It's going to be minus 1/3 multiplied by 1/3 minus 1/3 multiplied by 2/3. So in the end, I have 1/9, 2/9. So it's going to be minus 3/9. So it's going to be minus 1/3. All right? So this is the Jacobian. But we know in the formula of change of variables, I'm supposed to plug in the absolute value of this 2 by 2 matrix determinant. Okay? So instead of plugging in minus 1/3, I have another pair of bars right here. That is absolute value, as we agreed upon last week. Right? So I have actually two pairs of bars. One pair of bars is talking about the determinant of 2 by 2 matrix. The other pair is talking about the absolute value. In other words, remember this. Every time if you change the variables, you introduce a new pair, and then you have this Jacobian factor as the actual factor. This factor has to be always positive. Remember that. It'll be even easier to compute from 0 to 4, from 1 to 4, u divided by v plus 1 divided by 3 multiplied by 1/3 du dv. And you can actually do the following. The following work is completely single variable calculus because this is a cube in u and v. This is a cube in u. You have two numbers for u, two numbers for the other variable. So this is actually a cube. You find the antiderivative, and this is what you can get. Okay. But unfortunately, the number is surprisingly large for this kind of questions. I don't know why they spend such effort to ask you to compute large numbers. So this is the answer. Okay, so this is the final answer for this double integral. So a couple of remarks I want to make. Yep.
Why is it cubed?
Why is it
Should it be 4?
Oh, sorry, this is the 4. I don't change anything about intervening functions. The only factor I have to add in is the Jacobian factor. Okay. Jacob. Any French here? You know how to say this word in French? It's actually a French name. Jacobi is the name. Anyway, so up to this step, we are testing calculus 3. So all the following work, it has to be single variable calculus. You can in fact separate it into the product of two single variable integration. Okay? So a couple of remarks. First one is this factor is so important. You have to remember this all the time. You can change the variables. And you remember there's one extra factor as the Jacobian factor. And the way of computing this factor, you have to have a pair of equations where you can represent the old variables in terms of the new variables. Okay? Having these two equations is not sufficient to derive the Jacobian factor. Are you with me? You have to derive these two equations where you can represent x in U and V and y in U and V, so you can compute these 2x2 matrix determined. You have to remember the Jacobian vector, but also you have to represent x, y in U and V. Okay, so that's the way of deriving that. Second remark I'll make is I will give you very similar questions in this one, but the numbers will be much more friendly. You don't have to worry about it. Okay, and as I also mentioned this in several occasions, if you're doing a homework, keep your workbook with you. Okay, so that will force you to write your mathematics in a rigorous way. Okay, you don't want to scrap all over, especially if you want to come up with this kind of number in the end. You have to be super careful in every step, right? You have to be very sure the mathematics is correct all the way along in order to end up with the correct fraction here. So have your notebook clear, and in case you cannot come up with the exact number in the end, you can bring your notebook with me, and I will give back the points you deserve. Okay, and at the end of the whole semester, I will have several weeks of window. You can come up with me the notebook you have been written for the whole semester. I will even trace back to the original homework assignments to change your grade. Okay, are with me? So you can give me your workbook in section 13.2, and you only get 20% in that section. But I see all the work in your workbook. I can still give back the other 80%. Okay? So that will force you to, I give you some merits to prepare better for the final and for the midterm. So I want to practice a couple of more questions in changing variables. Yep.
I'm so confused. How did you get that U and the V?
Oh, the way of choosing the new variables. Okay. Here's the point. If you have a pair of old variables and x, y, right? You want to introduce a new pair of variables, U and V. You can introduce the new variables arbitrarily. You can let U to be equal to x squared plus y. You can let your V to be e to x. You can introduce a new pair of variables arbitrarily. But the problem is I have to make sure this new pair is useful here. All right? It is related to the problem somehow. And a way of doing that is if I look at the boundary defining functions,